I have a spring here, and Kenrick will produce a periodic wave on its left end. The wave travels down the spring, and when it reaches the right end of the spring, it gets reflected and comes back. The reflected wave interferes with the incoming wave, and when condition is right, we get a standing wave like this. I guess it's called a standing wave because the wave does not look like it is traveling to the right or to the left. The wave looks like it's just oscillating up and down without going anywhere. We say that the spring is oscillating in loops. Right now, there are 3 loops. And when I say the condition is right, I mean the source frequency, the frequency of Kenrick's hand, matches the spring's natural frequencies or resonant frequencies. If you remember resonance back in the simple harmonic motion unit, you know that when there is resonance, energy in an oscillator can build up easily. For example, when there is resonance, the source does not have to move up and down very much to make the spring oscillate with large amplitudes. But if the frequency of his hand does not match any resonant frequencies well, the spring does not oscillate in loops and energy does not build up well. So between 1 loop and 2 loops, there's not a lot of energy building up. At the lowest resonant frequency, the spring oscillates in 1 loop. He can increase his frequency, and the next resonant frequency would give him 2 loops. And then 3 loops. And 4 loops. See if you can get 5 loops. Good job, Kenrick. Standing waves are results of interference, the interference of 2 identical periodic waves. Here we have the light blue wave traveling to the right and the red wave traveling to the left. If we use the superposition principle to add the 2 waves together at any moment, we will get the dark blue interference result, which is the dark blue standing wave. Notice that there are 5 red dots stay still at all times. Those dots are called nodes. When we draw standing waves on a string, instead of drawing the rope at one moment, we often draw it this way to show that the string oscillates in loops. The points with no oscillation are called nodes. The points oscillating with the largest amplitude are called antinodes. Since there is no vibration at a node, I can touch a node and the vibration can still go up. However, if I touch an antinode, I can mess up the standing waves. Because one wavelength is always the wave going up, down, and then back. The length of one loop is always half a wavelength. So, one loop is always half a wavelength. You shall find this very useful for standing wave problems. Now let's look at the natural or resonant frequencies in a string. Unlike a spring mass system or a simple pendulum that only has one period and therefore one frequency, a string can have an infinite number of resonant frequencies. A string can oscillate in 1, 2, 3, or any whole number of loops. The lowest resonant frequency has 1 loop, and it is called the fundamental frequency or first harmonic. 2 loops would be the second harmonic, 3 loops the third harmonic, 4 loops the fourth harmonic, etc. If we count the overtones, we only start after the fundamental frequency, so the second harmonic is the first overtone, the third harmonic is the second overtone, and then the third overtone. For the fundamental frequency, if the string's length is L, in the length L there is 1 loop, so L equals to the length of 1 loop. And 1 loop is always half a wavelength. For the second harmonic, in the length L, there are 2 loops. And each loop is always half a wavelength. Since a loop is always half a wavelength, the length of a loop is always proportional to lambda because 1/2 is always a constant. In this case,
the length of a loop is half that of the fundamental frequency. So the wavelength changes by a factor of 1/2 because the length of a loop changes by a factor of 1/2. And because the speed is frequency times lambda, we can compare these three numbers. For these two, first harmonic and the second harmonic, which of these three numbers do you think is the same? The speed, frequency, or wavelength? For the first and second harmonic, the speed is the one that is the same because it's the same medium. It's the same string under the same tension, so the speed is the same. That means if this one's wavelength is halved, that must mean the frequency has to be doubled because 2 times 1/2 equals to 1. So if wavelength is halved, the frequency must be doubled in order to keep the speed the same. That means the frequency for the second harmonic must be twice the fundamental frequency. If this one has a frequency, that's what we call the fundamental frequency. For the second overtone or the third harmonic, the length of one loop, again, it is half a wavelength, which means it's proportional to the wavelength. The length of one loop compared to the fundamental frequency is 1/3 of that. So the length of one loop changes by a factor of 1/3. That means wavelength changes by a factor of 1/3 because speed equals to frequency times lambda, just like before. The speed is the same. That means if the wavelength changes by a factor of 1/3, the frequency must triple. So the third harmonic must have a frequency that is 3 times the fundamental frequency. Of course, then for the fourth harmonic, because the length of a loop is 1/4 that length of the loop, that means the wavelength changes by a factor of 1/4 and the frequency must quadruple. So this fourth harmonic must be 4 times the fundamental frequency. And then, of course, the fifth harmonic will be 5 times the fundamental frequency. So the nth harmonic with n loops must have a frequency that is n times the fundamental frequency. So if a string's fundamental frequency is 100 Hz, its overtones will be 200, 300, 400, 500 Hz, etc. The nth harmonic will be n times 100 Hz.